All right. What I said was that now that you know enough, about velocity, forces, and moments from last term, we can mix it with the stuff that we've learned today. Um, yeah, and check out what happens there with pressure.
Sir, any formal assessments of physics?
Mm, not this week. Maybe next Friday. So that I really want to like consolidate your knowledge.
So is it only the second term stuff we were studying or the first term also?
No, don't worry now. Today, we are going to mix up, we are going to, solidify our understanding of pressure difference, and then connect it to um, forces, mass, and acceleration, and velocity also, right? And then we are going to keep doing that now according to schedule. Okay. Revision week, formal assessment. There's anyway a formal assessment in March between 8th and 12th. So before that, we'll have another test, right? Yeah, we can do some stuff. Cool. Yeah, I think we'd better start. So now yesterday and day before we studied a variety of equations. No? There's pressure equals force over area. If you have pressure and an area exposed to that pressure, it will feel a force given according to this equation. Then we also found that pressure, actually specifically pressure difference is uh, in a fluid, there's a pressure difference when you go inside H2O, right? That is the value. Then we also figured out the density is equal to mass over volume. Yeah. Okay. Now today we are Let's take a look at what I was discussing. It was hydraulics, right? Now I just want to remind you that in here, if you have a pressure difference, there will be a difference in the liquid level. And the difference in pressure is, now let's say this is P1 and P2 pressure, right? Then clearly P2 is great, P1 is greater because it's pushed down this liquid. So it's P1 minus P2, which is equal to the, HOG. Yeah,
So should we draw that, sir?
No. Just to recap knowledge. All right. Yeah, I just want to remind you that. Okay. So let's take a look at hydraulics. This is an interesting application of pressure, right? Now, you may have seen this, in the Caterpillar trucks and on, right next to the, yeah, there are these arms that control, and right next to this, there are these things which look like a syringe, like the moving stuff. So, as in, when the caterpillar moves, this arm, this one will go forward and backward. So it's present here. It's present in the braking systems of cars, and yeah, it's a method of multiplying force by using the idea of pressure, right? Um, yeah. So using pressure and area to multiply force, right? So we'll study in the context of a car braking system. Okay. Now, this is the, now please write this and draw. This is shoe, okay? And this is the brake pedal. I'm going to mix in some moment question here also. Here, draw a cylinder with a piston, okay? And this one, here draw the wheel of the car. Hold on. We need to modify this. Put a piston in here. No, we'll actually simplify it. Just make this into a kind of a deal like this. And then there's a tube coming from here and go. Have you guys already drawn this bit?
So I do it up to the. Wait, sir.
Because if not, if you can make this smaller, that would be fantastic. Okay, just because it's not visible on the. That's the reason why I. Okay, if possible, try to make it like smaller than this piston. Okay. Okay. You guys draw this. I'll go and get a piston situation. The humble syringe. This is a piston situation, right? I just wanted to show. This is what we are drawing here. So there's a, right? Both of them have pistons. All right. Now, I assume you finished drawing. We'll try to work a little bit faster. Okay. Now, the concept here is that inside the tube, within this liquid, the pressure is constant, right? Equal pressure everywhere. Equal pressure everywhere. And then here, this piston area equals 4 square centimeters. Piston area equals 4 centimeters square. Right? That's this piston area. This one's piston area is 32 centimeter square, right?
So what's the piston, sir?
Piston is this part of the syringe. This is a cylinder and this is a piston. And piston cross-sectional area is the area that you are seeing here. Area of the circle, not this. But wait. Yeah. It's the, even though it is shaped like this, like a cone, the effective cross-sectional area that the pressure is hitting is this circle only. This circle. The area of this circle. The cone shape doesn't change any of the physics. All right. Now, this is just for revision, remembering. Here, we'll call this, this is A and this is B. Yeah? So the pressure at A equals force at A over area of A, right? And that is equal to, wait, we can do like this, no? Pressure at A equals pressure at B. So that means equals const. That is force at A over area of A equals force at B over area of B. Right? Now, when the driver pushes on that thing, on the brake pedal, let's say he exerts a force of about, wait, when is this from? About 10 Newton, no, 10 never, 30 newtons, right? Given that force A equals 25 Newton, let's say that's a reasonable value, right? 25 Newton. Now we have the areas also. Let's solve for force. Sorry, had a bit of an internet issue there. Yeah, so as I was saying, it is given that the driver pushes on the brake pedal with 25 Newtons of force. All right. Let's calculate the force at B, right? So let's do it. All of you are still here. Okay, one person is missing. Anyway, the force at A, that's 25 Newton, divided by the area of A, which is 4, is equal to force B divided by the area, which is 32. Now, you would have noticed that I didn't bother to convert centimeter squares to meter squares. So it's a special trick. Okay, if the same quantity area appears on both sides, you can put any unit you want, but assuming that you are using the same unit for both quantities, because the unit will cancel out. No. This unit here, centimeter square, is going to cancel out. So, like even if you convert it to meter square, that means times 10 to the power minus 4, that times 10 to the power minus 4 is on the other side also. So we don't need to write it. Special thing. Right. Now see, calculate the force. 25 minus 32. Yeah. So force B is how much? It's coming 200, no? Can you calculate and see? See how magical that is. You press on the brake pedal with 25 Newton and you get 200 Newton at the brake shoe, right? So that's how you know, kind of weakly human being, even a grandma, 70-year-old grandma can stop a 60 kilometers per hour car with her foot. That's like, sounds like a, you know, crazy thing to do, but with the power of hydraulics, it can, because they use the concept of pressure. This thing is so cool that it's used for all kinds of machinery and robots. But the cylinders and the tube must be very strong. I remember yesterday's one where they put a long tube going high up and broke the jar. So they are actually, since the area that if you notice that that jar is like a curved thing, so there's a lot of area. So there's a lot of force developed there, which is why it broke. At the same time, this cylinder and the tube must be very strong, right? In fact, you know, one of my old students here at CIS, their entire like the family business is hydraulics, right? It's such a high demand thing. Now, how much have you written, Sanaya?
So I wrote the whole thing.
Whole thing? Who is still writing?
I'm writing.
So I got 0.8 newtons for the answer.
Can't be, you know. So FB is equal to, did you cross multiply properly? You want to get rid of this guy, so you
Yes.
yeah. So it's 32 times 25 divided by 4.
So since so you put 4 into 10 minus 4,
No,
so
no, no.
I used that.
No, you misunderstood me now. This is centimeter square. If I want to my point was, even if you convert it to meter square, it doesn't matter. Like, for example, centimeter square to meter square, you multiply by 10 to the power minus 4. So
Yes, sir.
yeah. So you would have to put that same factor for both sides, but there's no use doing it, no purpose, because anyway it's going to get cancelled out, which is why I left it as centimeter square, because normally we put the unit also, no? SI units, no? But here you can see these two will cancel and you will get FD directly in newtons. Those who are writing, please let me know when you finish written, okay? Otherwise, we are just sitting here like idiots silently. Still writing. I should pause the recording. You know, when you're done, please. While you are writing, I'll just quickly re-explain. So the pressures here and here are equal. Pressure equals force over area. So that's force at A divided by area at A. That's pressure at A. And pressure at B is force at B divided by piston area of B. So we are given that the person exerts a 25 Newton force. And we are supposed to find the force exerted on the brake shoe here.
Sir, I'm done.
Okay, is anyone else still writing? No, right? Okay. So you
The
can
pressure is like equal, sir, because of like when you insert, like when you exert that way, its output also is same, right? So both
I don't
because of
understand
that.
what was that?
So like the pressure is same, sir, because like why is that, sir? Where pressure is same in the like in the wheel and when you exert.
That's how a liquid acts. It's called Pascal's law. So he found that within a liquid, the pressure is transmitted very efficiently from one place to another. For example, if you have a now see, there's a difference between water and air. Okay. Now see, this is full of air. If I block it with my finger, I can still push this in, right? And then this air is, super compressed. In fact, here, listen to the sound, right? But if you put liquid inside this, you can try and try and try. You're not going to be able to push this at all. So now liquids transmit pressure very well because they cannot compress, right? So then if let's say you have a 100-meter long tube that is full of water and you exert a pressure on one side, immediately it's going to be felt 100 meters away. So it's just that it's a property of liquid, right? Because of their, rolling over each other, molecules rolling over each other kind of nature. Okay.
So it's only in liquids, no sir, but not in the other
Not
states.
not in gases. Gases are too compressible, so they can't efficiently transmit pressure from one place to another. Solids don't, they can't move, no? So solids are good for short distance. For example, in the car, the gears transmit force from one place to another over short distance and very instantly. Come on, right? Okay. Hold on. Right. So using this apparatus, by using different areas distance, you can get different forces. Give me a second. All right. Now let's include some questions about force and acceleration also. Now we got the value of 200 newtons. Huh? So part B, due to the action of the brakes, the car decelerates from 20 meters per second to 5 meters per second in 0.76 seconds. Number one, calculate the acceleration. Calculate the acceleration. Then number, I'll do the answer here. So number two, calculate the frictional force. Yeah, calculate the frictional force that no, frictional force on the tires by the road. So the mass of the car is given as 2016 kilograms. No, why are we complicating our lives with unnecessary numbers? No, 2000 kilograms. Okay. So recall the equation. Now, if you can't recall, you have to call it. Sorry, deceleration. Deceleration. Now, since it's a reduction in speed, whatever value you get, if you get a negative value, when you write the final answer, put positive. Huh? Yeah. So acceleration is final minus initial. So that's 5 meters per second minus 20 meters per second. Change in speed over the time taken, 0.76. So let's calculate that value. $19.7. Yeah, 19.7. Then yeah, this one.
Yeah, I put minus since it's deceleration. Is it okay, sir?
No. Here's the thing. Now for acceleration, you will get a minus answer.
Yes, sir.
So oops, sorry. Yeah, for acceleration, you get a minus answer. But here they've asked you to calculate the deceleration. No? So deceleration is negative of acceleration. So they are expecting a positive value there. Right? So deceleration equals 19.7 ms minus 2. Nothing to worry yourselves about. Okay. Because even though now I'm trying to teach you about vectors. Even if you put minus, they won't cut marks like that. But it's like that. The acceleration, deceleration like that. Okay, now who can remember how to calculate force when you are given mass? Go.
F equals ma.
F equals ma. So that's 2000 into 19.7. That's 39,400 newtons. Now you must be wondering, how did applying 200 newtons on the brake shoe cost 39,400 newtons? That's a valid question. So what actually happens is, no need to draw this bit. What actually happens is when the brakes press on the wheel rim, it kind of stops the wheel from moving. Because of that, the rubber of your tire is getting rubbed on the road. So that rubbing, so it's basically like, just causing the situation that will enable these to rub together, right? Now I know from experience that a small fault in the brake shoe can cause a very large force on the vehicle itself. Yeah, right. So that is just enabling the tire to stop rotating, and at that point the road will take care of the rest. That's why you get your tires replaced every so many years, because after so much braking the rubber gets worn off, right? Okay, that's the first part. I'm going to give you another follow-up question on this. I hope finish writing this number one.
So one second. Okay.
Number 3 is to calculate the distance travel. Travel while braking. So for this, there's a special equation with acceleration and distance. Kind of hard to remember. That is v squared equals u squared plus 2as. I wonder whether this will give a wrong answer. Minus v squared minus u squared minus. Yeah. Anyway, you guys write this. I will just see whether it makes sense in vector form. Acceleration. So acceleration was 19.7. Yes. Minus. No, it doesn't affect anything. No? Same direction. No. Okay, you can still get the answer. Right? There are two equations of acceleration, one involving time, one involving displacement. Right? Now, shall I erase this bit? Yeah.
So you only wrote one question of the two we already wrote.
Yeah. I only wrote this as part B. It's part B3. So for this you will use. Now remember V is final velocity, u is initial velocity. So 5 square equals 20 square plus 2. Now here it's totally optional whether you put positive or negative. Okay. But the correct way to do is no, it's actually you guys can benefit from this because we use this in momentum. Okay. So you see, you take the everything going to the right as positive, everything going to the left as negative, right? So see the velocity. Let's say the car is traveling this way, right? So it goes from 20 to 5. These are all positive, substituted positively, but the acceleration is the force and acceleration is acting this way. That's why we are the real way to do it is to put negative here. Then only you will get a positive answer for S, right? S is the displacement. All right. Let's go ahead and do that. That's I think 20 square minus 5 square over 2 into 19.7 minus 5 square divided by yeah, divided by 2 into 19.7. We are getting as 9.52 meters. Seems a bit unrealistic. Maybe I was, too optimistic with this time. In reality, when you break from 20 meters per second to 5 seconds, you travel about, well, if you break really hard, maybe this is possible. Yeah. All right. Okay. Now that's motion that we kind of revised. I want to take a look at momentum also here, right? Well, momentum moments. Interesting. No, we can't have moments here. Ne? We could, just a little bit. Huh? Part B done? This anyway you wrote down at first. This part also quickly finish it, then we can look at the moment of the brake pedal in more detail. Anyone still writing this? Okay. Yeah. Part C. The brake pedal is shown below. No detail. Brake pedal is about this much. let's say 16 centimeters. And the force exerted by a person, the force of the foot, is being applied at a distance of, say, yes, right? That's the pedal, that's the foot. Okay. So during braking, the person exerts 25 Newton while the spring exerts 10 newtons. No, make that 8 newtons of force, right? Calculate the resultant moment. Calculate resultant moment. So we can calculate clockwise moment. Which one of these now? We haven't drawn the force due to the spring, no? This is F spring. And this spring is midway between the, it doesn't look like that, no, in the video. We'll just correct that. All right. So here you can calculate in Newton centimeter, no problem. So clockwise is this one, isn't it? The foot is trying to move it clockwise. So that's 25. By the way, moment equals force into distance from pivot, perpendicular distance from pivot. So 25 times 10. That's 250 Newton centimeters. Then the anti-clockwise equals that force into that distance. That's 8 into 10 centimeters. That's 80 Newton centimeters. So therefore, now this is clockwise moment, anti-clockwise moment. Resultant is the difference between the two, no? In the direction of the large one. So resultant moment. Resultant moment equals 250 minus 80 is 170. 170 Newton centimeters. Oops. Yeah, I think that's enough for now. But I will note down. Yeah, I will note down what is remaining next time. We need to explore some concepts. Momentum, no? Momentum and spring constant. Oh wait, you don't have spring constant, do you? Yeah, that's definitely enough for today. Okay, so just revising moment also. It will only be an object can only be in equilibrium if resultant moment is 0. That is the principle of moments. That means when object is in equilibrium, clockwise moment equals anti-clockwise moment. Also, the resultant force should be 0 as well. Okay. You must be wondering, but the dissection of that is too difficult for you guys at this stage. So that's done in A levels, right? Because here we have, forces in different directions. No? It becomes hard to solve F equals ma. You have to solve it in two directions, kind of. Yeah? All right. Okay, you guys casually finished writing. I'll just be doing the attendance. Okay, if you have a question, you can ask.
So how do you get 25 and 8 sir, for that force? Sir? So you're muted, sir.
Sorry, those are given in the question.